You see the title, and it is a paper by my friends from Belgrade, two faculties, mechanical engineering and transport and traffic engineering. You already heard about the title, so let's go to the second slide. Smart here does not mean clever, but it means separating, morphing, and adaptive remeshing technology. But we kind of played with the words because it is really also a clever technology to simulate fatigue crack paths. And here I will present two case studies. Both are aeronautical components and both have complex geometry. One is high temperature and pressure turbine casing, and the other is torque link and in landing gear assembly. Both cases we actually seen crackings. They both experience some cracks, and numerical methods were here used to simulate those cracks to find out about the number of cycles, of course, as the main goal, but also to find out if crack paths are simulated in a proper way. So next slide, please. This technology that you can see now on slide with more proper writing with dots after each letter relies on so-called unstructured mesh method, and it is implemented in ANSYS workbench, which we use we have used it in recent years. It's based on stress intensity factors evaluation, so it's linear elasticity, and path of crack growth is, of course, one of the most important issues here. This method also includes Paris law model as the simplest one. There are some big issues in way how to evaluate C&M coefficients of Paris law, especially in the case of materials that were already exploited and probably have different C&Ms in comparison with the new one, and of course also especially for quite advanced materials which are used especially for this high temperature and pressure turbine case. Next one. Here are some comparisons, not going into details, just let me say that this smart technology is part of the classical FEM, contrary to so-called XFEM. XFEM is extended finite element method, which has big advantage that mesh does not need remeshing. So cracks simply goes through the elements, and that was a leading technology or method of calculation for maybe a decade or more. That was built first in Abacus, then also in ANSYS, but then ANSYS came with this smart solution, so that actually a mesh is remeshed in each crack growth step, which is of course not done manually. That would be practically impossible, but it is done automatically, and this was the major advancement in this classical FEM application. Without that, you simply can't do it. Next. Here, just the basic equations that are used along the way, how actually interaction integral based on, of course, J integral is used to, but in linear elasticity to calculate stress intensity factors, and you can see some expressions. Next one that are built in, and also for fatigue expressions, including direction of propagation. We are not now concerned too much about it. It's simply built in the software, but it's good to know how it is done. Next. Now we go for these two case studies. The first one is damaged torque link. You see this Cessna and its torque link. You can see also a crack. It's 5 millimeters long and it is a surface crack. Next one. So numerical methods, as explained, smart FEM. You can see geometry, how it is created on the left. Then finite element mesh, which you probably cannot see. There are too many nodes, so they are not visible. But if we could enlarge this, you could have seen them. Then some nice color pictures of deformation and stresses. So stresses are highest in the critical area. You can see it in red, and also you can see crack initialization as done by numerical simulation. Next. You can see now crack growth, and if possible, if you, yes, that's what I wanted. Great, thanks. So you can see how crack grows. It's not a big deal here to get a good agreement between experimental, real, and numerical simulation, because crack will go straight forward, but location is important. It was really important to get numerically exact location, and so we did. Based on this, we could calculate, of course, number of cycles, which is of utmost interest, but not for this conference. Next one. Now you can see why this was done. The idea was to make a lighter component by 3D printing technology, and you can see this modified geometry and optimization, so-called topological optimization. So we did this with utmost aim to get a lighter component made of printed material, and to have it ready for the case of failure. Next one. And here are some comparisons for different geometries so that we could pick up the best one. Next one. Next slide, Francesco. Okay, just the numbers, not important very much for us. I think we should now go for the next one, next slide, because still we have a simulation here. Again, okay. Okay, now let me, yes. What is point here? After we did what I presented, we did another simulation, and that simulation was with the latest option that ANSYS Workbench is offering, and that is to simulate crack growth without initial crack. That's something very new, even for us. So we just present here the simple result that we obtained. You can see that there is no crack, you see, and only now it happens after a number of cycles. And you can see that crack path is now somewhat different, but almost the same. So not a big deal, but at this point, I just want to emphasize that this is something quite new that is at our disposal when we use ANSYS Workbench. And now I think we go for the second case study. So next slide, please. Damaged high pressure turbine case. This is interesting example from real world, from some aeronautical components that were not supposed to be cracked. And actually, these cracks did not come from the loading itself and from natural causes, but they came from wrongdoings in a workshop. Namely, this component, which is, you can see, very complex in shape, was there was some need to use EDM to make something. I don't really know what, but the man who did it wrongly, and he left a couple of notches or marks. And next slide, please. You can see them better on the next slide, at least in this schematic way. There were 9 of them. They practically damaged this structure, although they went unnoticed at the time. Next slide. And it was in non-repairable area. That's also important. Next one, Francesco, please. You can see them, some of them here as they were. You can see the list of them and their sizes as they were just marks. But then after 2,700 or something cycles, when this component came back to the workshop, they discovered cracks. In each case of these EDM marks, there were cracks. And you can see the sizes. The biggest one was 1.3 millimeter. So that was quite an experience. You made scratches, and then after a number of cycles, you get cracks. So what to do? They are not repairable. Question was, can this component work for at least another couple of thousands of cycles so that we don't stop flying? Because it was not repairable, and also they didn't have a spare part. So next one. Therefore, numerical simulation was applied. Not to go into many details, not an easy one, because the thermal loading was first applied to get temperatures, and then from distribution, spatial and time distribution temperature, there were stresses extracted so that we could find and simulate fatigue crack growth. Next one. You can see now here how the crack was modeled with a notch and initial crack of 0.1 millimeter. And if you click on bottom right, you can see how it advanced, and that was about the same as in real component. Next one. Next slide, please. Now, not only this crack was simulated numerically, not only, as you can see on the left side with the notch and the initial crack of 0.1 millimeter, but also with the crack of 2 millimeters without a notch. The idea was to compare them and to find out what is it also a problem for this component to have a fatigue crack without a notch. So, because to find out about that, we did a couple of numerical simulations, as you will see in the next slide, please. So on the left is a notch plus small initial crack. On the right is crack of 2 millimeters, initial crack without a notch. You can see crack shape and front and crack path after a certain number of cycles. Next one. And here from the other view, you can see the same, left and right once again. Notch to the left, no notch to the right. And both are simulating quite well the real event. And next one, just the same, but after increased number of cycles. Now you can see on the left it's 11,479 cycles. On the right is 25,575, so 2 times more and still a couple of cycles more. So next one, please. And also yet another angle of observation. And next slide, which is probably the last one, is about conclusions. We can say that smart technology as implemented in ANSYS workbench, give good prediction of crack growth path, although we still need experimental evidence and more detailed real events, but obviously it is a good one at this stage of development, and also number of cycles are always quite clear to quite close to the real ones, and that means that crack path has to be also correct. As I already mentioned, new version of ANSYS enable also to simulate initiation of crack. That's very important. And residual life of components, as I just said, is reliably predicted. So nothing is ideal in this world. The could be a big problem that this approach needs a lot of time. So that we were faced with that in the case of this high temperature and pressure casing. They needed answer for yesterday, and pure computation time was about 20 or more hours just for one run. Well, after one run, we could tell them generally what's going on, but in any case, it's not that simple that you just say, please, I have a problem, Houston, I have a problem, calculate this. And finally, of course, as always, for numerical simulations, we need more experiments and we need more examples to prove that numerical simulation is correct. Okay, thank you. That's all.